All right. So we're not quite done with chapter 5C yet. So let's get started on that. And then when we're done with that, we'll start 6. And today I also have a couple of fun videos for you, which is always kind of nice. First, let's go to Moodle and see what's going on over there. So I posted, I'm pretty far ahead with my posting now. I was worried that I'm going to forget something, but I'm quite caught up with it. So let's see what's going on there. So yeah, so we're still in C. We started that the other day, and we'll finish that now, and then we will go ahead to 6. But in the meantime, we've got a couple of videos to look at. See, what have we seen so far? What is math? What is history of math? What is 0? Why can't we divide by 0? Making sense of irrational numbers. Why are there so many numbers? And the golden ratio. All right, so we'll carry on. We'll have a couple more. These are not specifically tied to the subject matter of today, but they're still interesting to look at. And then there's a couple down here. There's one. This one is the infinite hotel paradox. Is a very interesting video about infinity, which we'll get to maybe next time. And then there's a nice discussion here about prime numbers, which probably, I guess we should have seen that a little sooner, but that's okay. And then when we get to that point, we'll also have a discussion about quadratic equations. So in the meantime, yes, Luke.
Hi. I had a question about the problem sets that you posted.
Yes.
When are those
due? Good question. Yes. Since I just gave them to you on Monday, I thought we could go over them next Monday. Okay. Now, these are not intended to be collected or graded. This is just practice. Okay. So what will happen is when we start on Monday, the first thing we'll do is go over these. And it will give you an opportunity to make sure that you're understanding what we're doing. Okay, and it's a pretty long one, but in spite of the length, it looks long. Well, let's just say it looks like it's going to take you forever to get it done, but no, it won't take that long. There's only 24 questions, and there's a couple of word problems at the bottom. Now, people are, for whatever reason, are worried by word problems. They seem to have had bad experiences in the past with word problems. So what I would just say with word problems is that what you're really trying to do is figure out what kind of, what you're supposed to do. In other words, is this question about prime factors? Is it about greatest common factors? Is it about least common multiples? Does it have something to do with any topic that we've covered? And if so, does it closely resemble any other types of problems we've already done? So it's really the challenge with word problems is trying to figure out what you're exactly supposed to do. But it has to be related somehow to all the topics we've been covering. It didn't just fall out of the sky. So once you catch on to what this is like or what it's all about, then it becomes very straightforward. Okay, so don't be panicking when you see word problems. Now, what I'd also like you to do while we're on the subject is there's altogether there's 3 of these. Now let's see, number 2, we definitely have covered this material. So I'll tell you what we'll do. Yeah, this is all about radicals. 100% about radicals. So here, I think what we'll do is next week, we'll go over the first problem set on Monday and this one on Thursday. Okay, that way you should have plenty of time to get them done. And then the following week, we can do the third and final problem set from this chapter. Number 3 involves what we're going to do today, which is not just the properties of exponents, but scientific notation and a new topic, which we haven't gotten to yet, which is about something called sequences. Okay, now once you've finished all 3 of these problem sets, you'll be extremely well prepared for the first midterm. The first midterm is based exclusively on chapters 5 and 6. So think of these problem sets as sort of a way of practicing for your exams. I mean, that's really what they're for. The exams will be very much like what you're seeing here, very much. In fact, when you see them, you might say, hey, wait a minute, did you accidentally give us the problem sets all over again? So if you can do these, you'll be fine on the tests, okay? Because it's the same material and they're the same types of problems. There won't be anything different, radically different than what you're seeing here. Okay, so that's where we're going to go with these problem sets. So remember that we'll do the first one on Monday, the second one next Thursday, and the third one the following Monday. Okay, and then when we're done with 6, we'll do the same thing, and then we'll start reviewing for the first midterm, which is probably going to take place sometime in the middle of October. Now, since we're online, you'll be able to do it at home. You'll have plenty of time. All right. In other words, it won't be like you're sitting in a classroom for 2 hours and trying to finish it all in a hurry. You'll have I think last year I gave everybody a week to get it done. And so you'll have time to go through your notes and review what you've done and watch the videos if necessary, and just make sure you understand what's going on. So it shouldn't be too bad. I mean, as long as you're following what we're doing, you should be fine. All right. So, but these will help you make sure of that. So when these are done, if you've gotten them, you're good. Okay. So they're kind of meant to be a preview, let's say, of what the exams will be like. All right. So with all that being said, let's get back to chapter 5. C, that is. And so we still have a ways to go. It's possible that we won't get to start chapter 6 today, but that's not a problem. We'll see what we can do. Okay, very good. So let's get back to where we left off. We were looking at the properties of, oh my God, what happened? Exponents. Yeah, that's more like it. All right, let's see. I think this is where we left off, right about here. Yes, this looks right. Okay, rules for exponents. Now, some of these rules, you may already understand them intuitively, but it's possible that you were not aware that these rules had specific names. Okay, so this is a good review because it's easy to forget how this works. Even with a calculator, you can forget what the properties of exponents are and what types of situations you might run into. So the product rule, as the name suggests, is going to tell us what we do when we multiply two exponents together. Now, you notice here that in both cases, the base is the same. Okay, remember, hold on 1 second. In an expression like this, oh, hold on, I just realized my my tablet is not plugged in. I can't write without the tablet. There we go. All right, here we go. I think I'm ready now. This is the base, and this is the exponent. And this, of course, the same thing is true here. This is the base, this is the exponent. So the key here to the whole thing is that if I'm multiplying two numbers together, as long as they have the same base, the result will be the same base. The exponent will be the sum of these two. Okay. That's what we call the product rule. Now, when I show you some actual examples, you'll say, oh, yeah, of course. But, you know, it's one of those things where we have to review and make sure that you still understand this. It's possible you've started to forget how some of these properties work. So we want to make sure that that is not the case. If you did forget, that's fine. We can pick it up now. So here's exactly what I mean. Let's look at this one. We have the same base. So what I've done here is actually I've done this twice. Once using the product rule, and once using another approach. So here's the product rule. I've added up these two exponents. And what that tells me is that 2 to the 3rd times 2 squared is 2 to the 5th, which is 32. If you go to your calculator and type 2 x to the y, 5. I think you need an equal sign. Let me confirm that of mine. I don't use this calculator all the time, so I have to double check. Let's see. I'm going to double check on mine. Oh, you can't. This, of course, is our friend, the Apple iPhone calculator, the scientific version, which you must have your calculator in what's called landscape mode in order to use it. If you have it like this, you're getting the basic calculator. Use this mode. Then you'll have everything you need at your fingertips. All right, so let's try this. 2, and the exponent is, use the exponentiation key, which is, you've seen before. It's underneath the M+ button. Hit 5. Okay, yes, this one does require an equal sign. And you should get your 32. Now up here, what I've done is, instead of using the rule, I evaluated each of these two terms separately. So 2 cubed is 8. 2 squared is 4. I multiply them together and I get 32. So what this is showing you is that you don't have to use the rule, but it might save you some time. Okay, so but this actually illustrates why the rule works. And by the way, if you had something like this, 3 squared times 4 to the 5th power, no, you can't use the rule, but you can still evaluate each of these individually. In fact, that's really the only way to do this. If you can't use the rule, for example, 3 squared is 9, 4 to the 5th power is 1024. And so you're just multiplying that by 9 to get 9216. And so here, the product rule can't be used because the bases are different. Okay, so down here, so in other words, what you're seeing here is the two equivalent approaches to calculating these products. If the product rule is applicable, you can go ahead and use it. If not, you have to use this approach. Just literally evaluate each term separately and then multiply them out. Now down here, we have something similar. We have 3 to the 4th times 3 squared. You can calculate that as 3 to the 6th if you want, or you can evaluate each one separately as 81 times 9. Either way, you'll end up with 729. Now, here's where it gets interesting. What if the exponents are negative or fractions? Well, you still are allowed to use the product rule. For example, how about this one? 2 to the minus 1 times 2 cubed. Now remember, 2 to the minus 1 is the same thing as 1 over 2 to the 1st, which is just 1 over 2. So the negative exponents do not mean that the number is negative. It means that you're converting it into a ratio. And so you've got a half times 8, which is 4, but look what you can do down here. If I add my exponents, I'll get 2 squared, which, as you know, is 4. Now, down here, I've got 4 to the 0 power. Now, this one is particularly simple because, as you know, anything raised to the 0 power is just 1. That's what I have here. So I end up with 1 times 16, or 16. Or if you just add the exponents, you'll just wind up with 4 squared, which is also 16. So what I think, just for the fun of it, I'm going to show you a slightly trickier example. How about if I have this? 5 to the 1/2 power times 5 to the 1/4 power. Ooh, what do I do now? If I want to use the product rule, I can certainly do so, But the problem is, what is this? 1/2 plus 1/4. What do I do with that one? Well, you might remember this special technique. You're searching for what's called a common denominator. So in other words, this can be written as 2/4. So therefore, what you're going to end up with is 5 to the 3/4 power. Now, that's a bizarre exponent. How do you solve for that on your calculator? Well, I'll squeeze it in down here. You need to do this: 5x to the y, open parentheses, 3 divided by 4, close equals. Now, let me confirm that on my calculator. I have to make sure because they're all different. I just want to make sure we only need one equal sign. Sometimes when you use parentheses, it takes care of itself. All right, here we go. 5. Oh, did somebody have the correct answer? Oh. Oh, that's all right. If you missed anything, you can watch the video. We're still doing exponents. Yeah, that happens. It's not that unusual. Sometimes the internet is cranky and you might get kicked out and you might have to get kicked back in. If that happens, you can certainly watch the video or just catch up with what we're doing. I don't know how much time you missed, but we're using the product rule. Okay, the product rule is this one, where you basically add the exponents if you have the same base. Okay, and so after that, we just started doing some examples. Anyway, so 5 to the 3/4 power. Let us try that. 5 exponent key, open parentheses, 3 divided by 4, close parentheses equals. Yep. No. Yeah, no, I guess that's it. It's a very unpleasant number, isn't it? I was expecting something nicer. No, I think I did it wrong somehow. Hold on one second. 5 exponent, open parentheses, 3 divided by 4. Yeah, it's kind of like 3.3437. Yeah, it probably would be better off expressed as a radical, but that's the actual value. I just made that up. That's why I didn't know what it was going to turn out to be. By the way, here's a helpful hint. If you've got a number raised to a fractional exponent, whatever the result is, has to be smaller than the base. So in other words, if 5 is raised to a fraction, the number that we end up with has to be smaller than 5. Okay, so, but anyway, the product rule always works. We don't have to worry about, for example, division by 0 or anything along those lines. All right. So let's see. The quotient rule. Now, the quotient rule is essentially an extension of the multiplication rule. If you have the ratio of 2 expressions with the same base, instead of adding the exponents, you're subtracting them. That's the difference. Okay, so remember, AM times AN is A to the M plus N. So in this case, now, by the way, here's the reason why this is working. Because if you had this, this is the same thing as A to the M times 1 over A to the N. And using the product rule, you would end up with M minus N anyway. So in other words, it's really the same thing. Technically, we don't need a separate rule for this, but it's easier to think of it in terms of products and quotients. So in other words, just remember, when it's a quotient, you subtract instead of add. Very good. Okay, now let's check it out. Let's see some examples. And in all cases, we'll do this in 2 separate ways. Once with the rule and once without. So here, if you did this without the rule, you'll see that this is equal to 32 over 8, which is just 4. If I use my rule, of course, my quotient rule, I've got 2 to the second power, which is, of course, 4. It has to be the same. All right. Oh, let me just leave that there for another second. Okay, now here's an interesting one. Because the exponent in the denominator is larger than the numerator, which of course implies that this is a fraction. 9 over 27 is a third. Here, if I use the quotient rule, I'll end up with 3 to the 2 minus 3 power, 3 to the minus 1. And remember, 3 to the minus 1 means 1 over 3. Okay, so if you have x to the minus n, just in general, that equals 1 over x to the n power. So again, the negative exponent does not indicate a negative value. It means that this is a ratio. All right. Now, the next rule is kind of interesting. And again, it really is just an extension of the product rule, but still it's important to see it separately. What happens in a case like this, where you've got an exponent which is raised to another exponent? Ooh, that sounds pretty complicated. Well, that's because it is. So what about this case? Now, what I'm trying to indicate here is that everything inside the parentheses, a to the m power, is then being raised to the nth power. And when that happens, we multiply these constants together. Okay, so let's say if I had 2 to the second raised to the third power, that would be 2 to the 2 times 3 power. Now, here's the reason why. Because this expression that you're seeing here is the equivalent of saying 2 squared times 2 squared times 2 squared. And if you use the product rule here, you'll see, oh, it's the same thing. That's why I said it really is just an extension of the product rule. Okay, so you just have to be careful with this one. All right. Okay, I think we're ready for some examples now. All right, so again, I'll do it 2 different ways. Here, you see what I've done is I've evaluated 2 cubed to be 8 before I squared it. But here I actually use the rule. Okay, 2 cubed to the second power is 2 to the 3 times 2 power. Okay, and then down here, you see what I've done. 3 to the 4th is 81, which when squared becomes 6561. Down here, I've actually used the rule because 3 raised to the 4th squared is then written as 3 to the 4th times 2, 3 to the 8th, which you can find in your calculator, is 6561. All right, good. Now, all of that was likely review, but it's possible that it's been a while since you saw this stuff. And so we need to make sure we really understand exponents before we go any further. All right, this is too important to neglect. It's kind of like scales when you're studying the piano. You can't really learn the piano without doing your scales. And it's hard to do math without exponents because they're everywhere. All right. Or it's like trying to be a painter when you can't draw. It doesn't work, does it? No, you have to draw before you can paint. So this is like the foundation. And so we want to make sure that along the way, we remember all the rules as we move on to the more advanced topics. Now, here's a blast from the past that you haven't thought about in a while. Scientific notation. Now, you learned about this in high school chemistry and physics. Most likely, the quantitative sciences use this all the time. Maybe biology too. Not so much. Biology doesn't really involve a whole lot of numbers, does it? No, but by physics and chemistry, that's all it is. It's really just math. It's especially physics. Physics is really maybe one of the most quantitative disciplines out there. In fact, that's one of the reasons why a lot of physicists ended up working on Wall Street, especially during the 80s and 90s, when the economy was really booming, because the money was so much better. And well, it's math. I mean, there's a movie which I can't remember the name of, but where one of the lead characters was actually trading for this bank. He was a quant trader, and he told the boss that, you know, I'm a physicist by training, but I'm doing this now because numbers are numbers. As far as I'm concerned, it's all the same. So yeah, science is, you know, it finds its way into many surprising areas, but the purpose of scientific notation is to express numbers that are either very, very small or very, very large in a very compact way. Okay, now we're going to do an experiment with your calculators right now, which I think you'll find interesting. Let's do this. Go to your calculator for a second. And I want you to see how it reacts to this. Let's see. Let me do it here first before I tell you what it is. I want to make sure, because every calculator is different, like I keep saying. Oh my God. Well, okay, I have to try another example. Oh, okay, maybe I have an idea. Okay, let's do this. On your calculator, it seems like a very simple problem. Let's do 1,000 raised to the 6th power. And don't forget the equal sign. Now, what does it say on your screen? Something you might not have expected. All right. Are you still in a state of shock? What does it say? Oh, come on. You know you have your phones right in front of you all the time. There you go. 1E18. What is that supposed to mean? All right. Well, that's what we're about to discuss. But I'll tell you right now, it's shorthand for 1 times 10 to the 18th power, which is this. Okay, now there's one with 18 zeros. 1, 2, 3, 4, 5, 6. Wow, that's a big number. So you see the motivation here. Would you rather write this number down on a piece of paper or this? This is just the calculator's way of expressing it, okay? This is pretty standard for almost every calculator in the market. It doesn't actually write out 1 times 10 to that power. This is what it means, E. It's understood that this means times 10 raised to that power. All right, now let's try another one. All right, one more, and then we'll be ready for this topic. How about Let's raise this to a negative power. All right, now in this calculator, let's see, I have to remind myself, like I said, I don't use this one all the time. There it is, okay. So put 6, but this time follow it up with this negative button. This button is what it's doing is it's turning this into -6. So this time we've got 1,000 raised to the -6 equals. So what's different this time? How is that screen different? Did it give you the same answer? No. There's something different this time. Oh, what happened? Well, this time it's 1.0 times 10 to the -18. It's a tiny, tiny number, okay? Because what you basically just did here is raise something to the -6th, or you can think of this as 1 over 1,000 to the 6th power. And it equals 1.0 times 10 to the -18. Now, this is what it looks like. Wow, that's a small number. So, of course, I think most people would agree this is the way to go when you have tiny numbers, tiny, tiny little numbers. So when the calculator reaches a certain threshold, from that point on, it always kicks into scientific notation. Now, this calculator has a very large threshold. I must say, it can show some really huge numbers before it starts showing you scientific notation. A lot of other calculators in the market don't go up quite that high, but this is a pretty good calculator. In spite of the fact that it's free, I guess iPhone wants you to be happy. They want you to have the ability to calculate very complex numbers. Okay, so now, how does scientific notation work? Well, first things first, whatever number we have, when we're done, we want a new number that has a single digit before the decimal point. And all the rest come afterwards. Now, once you've made that conversion, then we have to figure out what number to multiply it by to equal the original number. So here, for example, 1.22 has to be multiplied by 1,000,000 in order to be equal to the original value of 1,220,000. Now, it just so happens that 1,000,000 is 10 to the 6th power. So this is how we would write it, 1.22 times 10 to the 6th, because we're multiplying 1.22 times 1,000,000. So you start by making sure there's only one digit before the decimal, and then you figure out what you have to multiply this number by to give you back the original value. And in this case, it happens to be 1.22 times 1,000,000, or 10 to the 6th. All right. So now, just as a quick review, I've put together a little chart to help you remember the different powers of 10. Okay, so here we go. For example, and you can confirm these with your calculator, 10 to the 0 is 1, of course. Please remember, no matter what number we raise to the 0 power, it gives us back 1. Same thing with 10 to the first. Any number raised to the first power is x. Then it gets interesting. 10 squared is 100. 10 cubed is 1,000. 10 to the fourth is 10,000. 10 to the fifth is 100,000. 10 to the sixth is 1,000,000. Okay, so remember those. Now, here's a quiz for you, and these are names you hear tossed about all over the place. What is the exponent associated with 1 billion? It equals 10 raised to some power. What power do you suppose that would be? Ooh, are we getting rusty? Oh, I think we are. 1 billion is 10 raised to what power? Whoever gets it first, that tells me that you were paying attention in science in high school. Oh no. Do we have a lot of people here who not like science? I mean, that's okay. I was just wondering. 9, that's it, 9, exactly, ding, ding, ding. Okay, so Luke, you are at the moment the champion of scientific notation for the class. Well, then you probably know this one. Ooh. I see, I can feel the hard thinking coming through the computer. Everybody's frantically trying to remember. Oh no, I forget. How could this be? 12, that's right. Now, I'll give you a hint here. You all know this number very well. I'll tell you why. How much storage does your laptop have? How many gigabyte, how many byte, what is the storage? Is it, let's say 1 terabyte perhaps? Or maybe it's a little smaller, 500 gigabytes. Do you know? I mean, when you bought it, they must have told you. But let's say your hard drive has a terabyte of storage. 1 terabyte equals 1 trillion bytes. Now, a byte, if you've had no experience with computer science, a byte is a single unit of storage on the computer. It can hold 1 letter, number, or special character. So that means your hard drive can store 1 trillion bytes of information. Wow, that's a lot, isn't it? Which means that 500 gigabytes is 500 billion. So did you know this? Maybe not. When they sell your computer, they'll say, wow, look at this. It has a terabyte of storage. And then you say to yourself, well, that sounds impressive. Now you know what it means. 1 trillion bytes worth of data is on your hard drive, or at least it's potentially there. And now they're getting bigger all the time. You might have 2 terabytes or 4 or 8. It's amazing how much storage we have these days. Now, I'm going to show you a very fun example in history of when scientific notation might have come in handy. All right. So this is an example from economics, but you'll like it anyway. Watch this. When you see this, you're going to be stunned beyond belief. Oh, where is it? This is a note that was issued in Zimbabwe about 2008. What does it say on there? $100 trillion. What the heck? Well, in Zimbabwe, the inflation rate was astronomical. So it got to the point where $100 trillion would be enough to just about buy you a loaf of bread. So $100 trillion, let's see if I got space here, would be 1.0 times 10 to the 14th power. Okay, 1.0 times 10 to the 14th power dollars to buy a loaf of bread. Now that's a lot of inflation. And so this is actually not the world record for inflation, but it's pretty close. So yeah, that's pretty scary looking, isn't it? Yeah, they've just zoomed in on the number. That's not the whole bill, but still, oh, there it is. You can really see it better now. That was actually issued in 2008. Now that's a country with hyperinflation for you. But you can see sometimes we run into these gigantic numbers in the real world, $100 trillion for a loaf of bread. Yes. So if you've ever had an economics class, you know inflation is very harmful to a society. And so that was one of the most ridiculous examples of inflation. Anyway, what about the small numbers? Oh, before we do that, I just want to point out that let's get some practice here. We could write 124 as 1.24 times 10 squared because this is just 100. 2148 is 2.148 times 10 cubed because this is 1,000. And 32,154 could be written as 3.2154 times 10 to the fourth because this is 10,000. So remember, in each case, we only have a single digit for the decimal point. Okay. Now, oh, by the way, I have a fun side note for you here. And I only discovered this myself fairly recently. Let's say you had a number like this. Let's say you go to the store to buy something fairly expensive and it costs $1,000, let's say $12.42. And so this is what you would expect to see. You look at the cash register, 1,012.42. I guess I'd better take out my credit card. It turns out, surprisingly enough, that there are some countries in the world where the periods and the commas have the opposite meaning. And so in a country like Brazil, that same price would be written like this. I don't know how this could have ever happened. You would think that something like this would be standardized, but it is not. And in fact, I was actually in a Starbucks in Portugal, and I bought it at Starbucks for €3, and it said in the cash register instead of 3.00. But I already knew about this, so I wasn't shocked to see it. But yeah, this is not universal throughout the entire world. This is what we do, but there are several countries which have the opposite. Okay. Are you shocked and concerned by that? Are you disturbed? I just find it surprising that this could have happened. I mean, I guess every country has its own conventions, but you would have thought that math would have been the one thing where we all use the exact same symbols. And if you've ever been to a foreign country, if you look at a laptop that was built in any foreign country, the keyboards are not exactly the same because some of them need other symbols that we don't have here. So, but anyway, let's get back to this. Now, for the small numbers, we have negative exponents, of course. Now, these are a little bit trickier. So let's look at these. 10 to the minus 1 is 1/10, or 0.1. 10 to the negative 2 is 1/100th. And then we work our way down. This is 1/1000th. And we work our way down. This last one, I'll go skip down to the bottom. This is 1/1,000,000th. Okay, 1/1,000,000th. Now, here's a rule of thumb. I find this to be very helpful. You may not like this, and if so, you ignore it. But it can get very confusing with these tiny numbers. So if you look very carefully, and let's look at 1,000,000. These zeros that come before the first non-zero number are called leading zeros. Okay, so if you count all the zeros that come before the first non-zero digit, we call them leading zeros. And with an exponent of -6, you would think there would be 6 leading zeros, but if you count them, there's only 5. And the same thing here with 10 to the -5th, there's only 4 leading zeros. So the way to think about it is that for 10 to the minus, let's say n power has n-1 leading zeros. It's always one less than the exponent. Now, that's how I help myself remember this. If this doesn't work for you, well, okay, you try something different because everybody's memories work differently. The things that help one person remember are not the things that help another person remember. So you do whatever works for you, but I think this is helpful, okay? But I would never tell you that you must use this approach to remember these small numbers, okay? But I just happen to like it. So if you like it, you can use it too. If not, you'll find something different. By the way, just for the fun of it, here's another fun thing I was going to do, and I forgot. We saw in our previous chart that the numbers only went up to a millionth, and then we mentioned billions and trillions. Here's an interesting question. Let's try this. So we know that 1 trillion is 1.0 times 10 to the 12th. Oh, I forgot. This is kind of a nuisance in PowerPoint. But if you've ever wondered how to do this in PowerPoint, you have to tell it you want the font to be a superscript. All right, here's what I wanted to ask you. What comes next? After 1 trillion, there's a name. There's a name for many of these enormous numbers. The question is what? Like, what about 10 to the 15th power? This thing is really giving me a hard time, I can tell you. All right. What I'm telling you. Okay, what comes after a trillion? Does anyone know? All right, well, if you don't know, you don't know. It's actually called quadrillion. And so there we jump up the exponent to 15. And then what comes next? 1 quintillion. Okay. And then it does go on and on and on for quite a while. There's plenty of names. So if you're wondering, let's say that this has been keeping you awake at night worrying about this. Like, what do we call it if we have 10 to the 18th power? I don't know. Okay, so on somewhere out there on the internet, I think Wikipedia has this. Yeah, here we go. It has a nice little chart for us. Look at them. Ooh, look at these names. Quintillion, sextillion, septillion, octillion, oh my God. Now the one that's going to surprise you to no end, and there's actually a unit called 1 googol, which is 1.0 times 10 to the 100th power. Now you're probably saying to yourself, I've heard of a special company whose name reminds me of this. What company would that be? Well, you're not imagining things. Google is named after Google. Now, the people who invented Google or started it wanted to call the company Google, but they could not have copyrighted it legally because that word is just a number. So they changed the name slightly to Google, and now suddenly it becomes a brand name, which they can copyright and prevent anyone else from using it. So the company Google is actually named after 1 googol, which is 1.0 times 10 to the 100th. Okay. Now somehow it got left out. Oh, here it is. They did include it. Then they really get out of control. This Googleplex is 10 to the Google power. 10 to the 10 to the 100th power. Okay, well, all right, anyway. So I don't know when you would ever see that. I'm sure these numbers, like if you were to ask Google a question like this, how many atoms are in the universe? It's going, 10 to the 82nd power. So a Google is bigger than that, isn't it? Oh my God. So this is a fun fact. You want to save this for when you want to sort of, somebody who's kind of a show off, you want to save that and show off right back that you know what Google means and they don't. Okay. Yes. So anyway, so let's now look at the tiny numbers again. So now the tiny numbers, it's a little bit more of a challenging because you've got leading zeros, but remember, here's 1 leading zero. And therefore the exponent is -2. We have 2 leading zeros. Which implies the exponent is -3. Okay, 3 leading zeros implies -4 is your exponent. All right, so remember, the number of leading zeros as our rule of thumb is 1 less. This is only for negative exponents, that is 1 less than the exponent. Okay, let me make it clear here for negative exponents only. Okay, so that's taken care of. And so we're good there. Now, and by the way, when do you actually use these? The numbers have to get pretty big before you start using scientific notation for the most part. But there's no official cutoff point. But realistically, I mean, you wouldn't use scientific notation with hundreds or thousands. That would be ridiculous. But you might use it for trillions because you're getting into some large numbers. So there's no right or wrong way to do this, but usually when the numbers get large or small enough, you start using this because it's just easier. Like, here's a good example of what I mean. If you look at this number, you know what? You can see there's 6 leading zeros. So this is 9 times 10 to the -7. But I think you'll agree, it's easy to make mistakes when you're looking at a tiny number like that. This is clear cut. It's easy to see at a glance what this number is. I think once you start having so many leading zeros, it really is easy to lose track of them and make mistakes. So this is probably the way to go. Okay, it's just a way of making it simpler so that we don't make mistakes. Now, can we perform algebraic operations on scientific notation? The answer is yes, but we have to be careful because each number has two parts to it. It has an exponent, or a power of 10, I should say, and this number can be thought of as the coefficient of the expression. Okay, so we'd like to be able to multiply them or divide them or subtract or add anything as possible. So we're going to use the commutative property to show how to do this in a simple way. We'll start with multiplication. Now, by the way, I just want to mention you cannot add these together. Let's say you had something like this. The rules I'm about to show you would not apply here. You can't add these together because the exponents are different. You would have to formally evaluate these and then add them together, but you cannot use the techniques that I'm about to show you. These are different. So with addition and subtraction, in order to combine them directly like this, you need to have the same exponents. In other words, 2.0 times 10 squared plus, let's say this was my scenario. Oh, well, there's no problem now. It's just 5.0 times 10 to the second power. All I had to do was add these two together. Okay, but that's the only time you can do this. Instead, most of the time, you would have to actually evaluate them first and then figure out. And then if you want to, you can now write this as 3.2 times 10 cubed, if there's a need for it. But you had to go through the steps of formally evaluating it first. All right, then. Now here's an example, though, of multiplication. Multiplication is different. I can multiply any two expressions in terms of scientific notation that I choose. It doesn't matter if the base is the same or not. Like this one. So what we're going to do is basically rearrange these in a more convenient way. Oh, I see. So here I've got 2.8. And now these have the same base. So therefore, look how easy this is. And if I need to write it out, not in scientific notation, I can do it just as easily. Now, you know what? I'm wondering about your calculator. If you can actually ask it to type in a number in scientific notation, I'm going to look here and see if that works. What if I want it to say 2.0 times 10 to the third? I'm not so sure about that, but I'll tell you what, there is a key here. Let me show this to you. If you look next to the 1, there's a button called EE. If I wanted to, for example, type 2.0 times 10 to the third, which is 2000, on this button, what you would do is put 2 EE 3 equals, and there it is. It'll come up with 2000. So in other words, the calculator is interpreting EE as 10 to that power. I don't know if that's going to help you or not, but I just wanted you to be aware that this button exists. We might be able to find something interesting to do with it. In fact, we might be able to do some multiplications with it. Let me try this. Let's see if we can come up with this number. It would be 2 EE 3 equals times 1.4 EE to, I think that should do it. Let's try this. Two EE 3 equals times 1.4 EE 2 equals. Yeah, it works. Oh, you know what I just realized? I made a mistake down here on the bottom. This is not 28,000, it's 280,000. Sorry about that. Because that's what you're going to get up here. All right, so it did work. If you want to use that approach, that's fine. You don't have to. You can use, the usual exponents of 10, but it's, it's nice to know that it's there. Okay, so remember, EE means simply raise something, the 10th power, 10 to some power. All right, now as far as writing things out in scientific notation, though, I don't know if it has that ability. Like it'll do it automatically with large or small numbers. I don't know if you can force it though. I'll have to investigate that. Yeah. All right, well, anyway. So here we did exactly what I showed you earlier. This reduces to 2.8 times 10 to the 5th, which is 280,000. Okay. Or you could just leave it as 2.8 times 10 to the 5th. It means the same thing, of course. All right, so that wasn't too bad. All right, now let's do another example. Now this one has negatives in it, so let's watch it. So basically, always your strategy is to combine these coefficients and then combine the exponents. So now this is 4.5, of course. And here I'm using the product rule. Let me just throw this up here. And so 4.5 times 10 squared, you can confirm that on your calculator, is 450. By the way, I do want to mention one thing. You remember when you were first learning multiplication as a child, we used this as our multiplication symbol. And then later on, they sort of dropped it in favor of dots or simply no mark. In other words, if you saw something like this, 3xy, it's understood this means you're multiplying these together. Actually, let me do this. Anything like that, any algebraic expression. Well, with scientific notation, we typically continue to use the x to represent multiplication. Okay, so just be aware of that. All right, let's see. Now, what about division? Well, we're going to do exactly what you would think. We're going to divide the coefficients first, and then we'll apply the quotient rule on the powers of 10. Okay, so remember, don't forget, that's the quotient rule. Okay, now sometimes we may need to do some simplification though. If we run into an example like that, I'll point it out. So let's look at this one. Now, what are we trying to do? Let's divide these two, like you see here, and that's going to give me 4.1. With the exponents, I've got 10 to the 7th over 10 to the 5th. And according to the quotient rule, that's 10 squared. So 4.1 times 10 squared is the same thing as 410. Okay, now let's see. There's one more example here that we want to look at. This one is interesting because it involves a small number. Okay, 3.9 times 10 to the 5th is divided by 3 times 10 to the 8th. So the coefficients, the ratio of the coefficients is 1.3. But when you apply the quotient rule, ten to the minus third power. Now, remember what that means. This is actually the same as saying 1.3 over 10 to the third, 1.3 over 1,000, which is the same thing as 0.0013. Or you can think of it this way, 2 leading zeros result from this being to the minus third power. Very good. Now, I'd like to show you another example where we may have to simplify a little bit. Suppose I had something like this. Well, we know to multiply the 7 and the 5. And then we're going to multiply by 10 squared and 10 cubed. So we'll apply our rules. 10 squared times 10 to the third is 10 to the 2 plus 3. Now, you might say, well, we're done. But remember, we said that by convention, we only want only one digit before the decimal point. That isn't true here, is it? It's 2, 35. Actually, you know what? Let me do this. Let me write this as 35.0. So I would like to write this as 3.5 times 10 to some exponent. The question is, what exponent should I use? Now, if I convert 35 to 3.5, I have just divided by 10, which means in order to avoid changing the value of this expression, I have to multiply this by 10. So what did I just do? I divided this one by 10, and I multiplied by 10. In other words, they both mean the same thing. This is 3,500,000. And if you go to your calculator, it'll confirm that for you. But this is the preferred expression. We like to have a single digit before the decimal whenever possible, and the rest should come after. So while the two numbers are the same thing, and 35 times 10 to the 5th is not wrong, but it's just not in the preferred format. Okay, so just be aware of that. Now, if you do this on a test, I won't mark you wrong, but I just want you to be aware that this is the way to go. Okay, So that was pretty intense. And so now you've seen it again, and you will never forget again how to do scientific notation. All right, now I did promise you a couple of videos. Let's do that. There's one more topic coming up in this chapter, which is fairly complicated. So I don't want to rush into it. So what I'd like to do is show you some videos now. We're not going to finish, it looks like we're not going to finish this today. That's okay, we'll get to it on Monday. But I still want to do the first problem set next Monday and the second one next Thursday. The third one, by saving it to the following Monday, will be fine because that one requires us to do arithmetic and geometric sequences, which is the next topic. Okay. So, all right, let me go open up those videos. Okay, here we go. Now, like I said, the first one, actually both of these, they're just fun. They're not really related to what we did today, but you know what? The more you understand about the history of math, the more exciting I think you'll find it. Okay, all right, let's get this one going. Now, everybody remembers our old friend Pythagoras and the Pythagorean theorem. So I'm going to send you this link as usual and post it in the chat room. So let's check this out. I think you'll find it very interesting. Well, how was that? Like I said, that's not like we were doing the Pythagorean theorem, but you remember that from somewhere along the way. And pretty interesting. 350 ways to prove it, including 12-year-old Einstein. What does that tell you? It looked like he had a very bright future, huh? Why? Well, that's how math works sometimes. But the thing is, you never know what might result from one of these proofs. In other words, in the process of proving it one way, you might stumble onto something that gives you insights into another problem, which nobody's been able to figure out. So it's not a waste of time because you're thinking about this problem in different ways, and it could result in other very useful results. You never know. And of course, the Egyptians, as they said, were using it already to build pyramids and other things. And so you never know where this stuff will go. That's what entrepreneurs do. They take these ideas and they turn them into something useful. And before you know it, we've all got something better and they have lots of money. Okay. All right. Now, this next one, again, this is not really, strictly speaking, related to what we did today, but I think you'll like it. So we'll get this one going. All right. Let's stop that. And here we go. Let's check it out. All right, so I'll tell you what. So I think that will be enough for today. We got a lot done. So when we pick it up on Monday, we will go over the chapter 5 problem set number 1. And then we'll get back to the new material, which is the last part of chapter 5C, where we will learn about arithmetic and geometric sequences. And then if there's time, we'll start chapter 6. Okay, so for now, all you have to do is work on those problems from chapter 5 rather, the number 1 problems from chapter 5. And then I will see you all on Monday. All right. So have a good weekend.
All right, thank you, Professor.
All right, you're welcome. You're welcome.
All right, thank you. Take care.
Welcome. Bye.